Dear esteemed audience, today let us embark together on a truly wondrous and captivating journey of discovery, one that unveils the deepest mysteries of the universe through a groundbreaking theory that is fundamentally reshaping our understanding of reality itself: string theory, also known as the theory of strings. This is far from a mere dry scientific concept. It is nothing less than a gateway to an entirely new and extraordinary world, where everything from the tiniest particles to the immense force of gravity is interconnected in perfect harmony, much like a grand cosmic symphony that resonates endlessly across the vast expanse of existence. Imagine yourself seated in a dimly lit room, surrounded by the gentle vibrations emanating from invisible strings, and it is precisely these vibrations that give rise to everything we see, hear, and feel in our daily lives. That is the profound allure of string theory, an idea that has endured numerous ups and downs throughout its history yet continues to shine brightly, especially with the most recent discoveries in the year 2025, when data from powerful telescopes is providing the very first indirect evidence in support of this revolutionary framework. To present you with a story that is both authentic and profoundly insightful like this one, our team has invested countless hours in thorough research, meticulously connecting ideas drawn from vast mountains of scientific literature and documentation. Now, armed with a detailed script that exceeds 20,000 words in length, we are proud to deliver an independent documentary report, constructed on a rock-solid foundation and entirely free from reliance on any external sources whatsoever. This is not intended to be a rigid lecture delivered in a classroom setting. Rather, it is a genuine adventure, where we can all share in the excitement felt by scientists as they push the very boundaries of human intellect and comprehension. Let us begin right from the origins, tracing back to those earliest days when humanity first attempted to comprehend the tiny building blocks that construct the entire universe. Let us turn the clock back to the era of ancient Greece, when the term atom, derived from the Greek word atomos, was introduced to describe the smallest indivisible units of matter. This concept originated with philosophers such as Democritus, who envisioned the universe as an infinite sea of minuscule particles colliding with one another in the endless void of space. In modern science today, we refer to these as fundamental particles, the incredibly small components that form everything from distant stars in the cosmos to the very air we breathe in and out with each moment. But can you truly fathom just how minuscule these particles are? They are so extraordinarily small that, from the perspective of quantum physics, they effectively have zero size. They are described purely as mathematical points in space, possessing neither area nor volume, much like a single dot of ink placed on a blank sheet of white paper, yet this very dot serves as the foundational element for trillions upon trillions of atoms that combine to create molecules, cells, and ultimately our own human bodies. Picture a dedicated scientist working late into the night in a completely darkened laboratory, peering through the most advanced microscope available, striving to measure something far smaller than the wavelength of light itself can reach, only to realize that at such scales, all familiar notions of size and dimension simply dissolve away. It is a sensation that is simultaneously awe-inspiring and disorienting, akin to standing at the edge of an invisible abyss that defies all intuition. Yet, it is precisely this apparent absurdity that has given rise to a major contradiction in our understanding. How can the fundamental building blocks of the universe lack any size at all? How can they exist without occupying any space whatsoever? Classical physics would vehemently declare this to be impossible, but the Standard Model, the cornerstone of modern particle physics, nonetheless accepts it as fact. Within the Standard Model, particles such as electrons, quarks, and photons are treated as dimensionless points. Scientists employ these point-like particles in their calculations, and the results align with experimental observations to an astonishing degree of precision, often matching data down to many decimal places. However, the Standard Model is not without its flaws and limitations. It completely overlooks the force of gravity, which Albert Einstein so elegantly described through his theory of general relativity. When attempts are made to integrate gravity with the principles of quantum mechanics, everything breaks down at extremely small scales, where energy densities become infinite and the governing equations lose all meaningful interpretation. This is the critical juncture where a revolutionary new theory becomes essential to patch these glaring gaps, and string theory has emerged as a brilliant beacon of hope amid the surrounding darkness, offering potential solutions to these long-standing puzzles. Now, allow me to transport you back to the year 1968, pivotal year that marked the unexpected birth of this theory. Amid the vibrant and energetic atmosphere of European research laboratories, the physicist Gabriele Veneziano was diligently studying the strong nuclear force, the interaction that binds quarks together within the atomic nucleus. By chance, he discovered that the Euler-beta function, a mathematical formula originally developed for statistical probabilities, perfectly matched the characteristics of the strong force. He could not immediately explain why this was the case, but the thrill of that discovery must have felt akin to uncovering a mysterious puzzle piece in a much larger picture waiting to be assembled. Then, in the year 1970, physicists including Yoichiro Nambu, Leonard Susskind, and several others shed further light on the matter. If we imagine that fundamental particles are not mere points but instead tiny one-dimensional strings that constantly vibrate like the strings on a guitar, then all interactions could be elegantly explained using that very Euler function. These strings exist at the Planck scale, approximately 10 to the power of -35 meters in length, billions upon billions of times smaller than an atomic nucleus. At everyday scales, they appear indistinguishable from point particles, but they possess an internal structure, with their vibrations giving rise to all the diverse phenomena we observe in the universe. Nevertheless, the path forward was anything but smooth and straightforward. High-energy experiments conducted in the subsequent years revealed predictions from string theory that conflicted with real-world observations, while the standard model achieved triumphant successes one after another. As a result, string theory was relegated to the shadows, dismissed by many as a failed idea and consigned to the dustbin of scientific history. The majority of physicists turned away from it, with only a handful of persistent researchers, such as Joel Shirk and John Schwartz, continuing to delve deeper throughout the 1970s and 1980s. They labored in modest offices surrounded by towering stacks of papers, enduring the isolation of those who dare to challenge the prevailing consensus, yet the more they explored, the greater the immense potential they uncovered. Then, in the year 1984, the first major earthquake in the field occurred. A groundbreaking new paper was published, and although it initially faced fierce criticism, with physicists pausing their work to launch attacks, much like hurling stones at a small boat emerging after a fierce storm, something miraculous soon followed. Over the next 3 years, more than 1,000 papers on strings were produced. From a drifting vessel, the theory transformed into a shining star, and the British physicist Michael Green emotionally described it as a classical theory, arising from the utmost simplicity yet capable of explaining centuries of progress in physics. So, what exactly is string theory in its essence? Envision yourself holding a small string in your hand, shaking it to produce vibrations, and each distinct mode of vibration generating a different musical note. That is the core idea. Every fundamental particle is a manifestation of the vibrations of these ultra-tiny one-dimensional strings, no longer dimensionless points. They do not require volume because they are vibrating strings, thereby resolving the old contradictions surrounding size. Furthermore, the graviton, the hypothetical particle that mediates the force of gravity, is also a specific vibration mode of these strings, enabling seamless unification with the other three fundamental forces, the strong, weak, and electromagnetic forces. This makes it a comprehensive and complete theory, inspiring many scientists to dream of a true theory of everything that encompasses all aspects of nature. And by the year 2025, that hope has grown even stronger, as data from the Dark Energy Spectroscopic Instrument, DESI, indicates that dark energy is gradually weakening over time, aligning perfectly with string theory models where dark energy arises from string vibrations or additional spatial dimensions. However, the road ahead remains challenging and full of obstacles. From the year 1984 until 1995, the equations proved extraordinarily difficult, resembling an enormous stone wall that halted progress in its tracks. Physicists resorted to approximations, but numerous equations remained unsolved and open-ended. The theory entered a period of stagnation, with researchers standing on the shore, gazing at the boat but unable to board it. Then, in the year 1995, at a conference held in Southern California, Edward Witten delivered a shocking lecture that elevated the theory to what is now known as M-theory. This marked the second major revolution, unifying 5 distinct versions of string theory into a single coherent framework and revealing the existence of 11 dimensions of space. Witten, speaking in his calm and warm voice to a packed auditorium, explained the 11th dimension as analogous to the thickness of a membrane, which helps account for the strength of interactions. The 5 versions, Type 1, Type IIA, Type IIB, Heterotic O, 32, and E8 times E8, are merely different perspectives on the same underlying reality, much like the 5 states of matter sharing a common essence despite their differences. M-theory is also referred to as membrane theory, matrix theory, or even mystery theory, because even Witten himself has admitted that we do not yet fully understand it, comparing it to a gigantic starfish where we can only glimpse the tips of its arms. It requires 11 dimensions to ensure that quantum probabilities remain consistent and logical, and with a large coupling constant, the 11th dimension becomes crucially significant. In the year 2025, ongoing research into dualities and double geometries continues to strengthen the theory, with DESI data revealing dynamic dark energy that matches string models incorporating non-commutative spaces. Let us now delve deeper into how string theory resolves the contradictions inherent in particle physics. The standard model features 17 particles, each with seemingly arbitrary properties such as mass, charge, and spin. Treating them as points leads to chaotic infinities in calculations. In string theory, however, each particle corresponds to a string vibrating at a unique frequency. Closed loops of string produce the charge-neutral graviton, while open strings give rise to quarks, electrons, and photons. The frequency and tension of the strings determine all properties in a non-arbitrary manner. Mass arises from the energy of vibrations, in accordance with Einstein's famous equation E equals mc squared, rather than solely from the Higgs field. The Higgs particle itself is a distinct string mode. Electric charge emerges from how the strings wrap around extra dimensions, potentially in fractions like 1/5 or 1/15. The 3 generations of particles, similar but progressively heavier, explained by longer wrappings within Calabi-Yau spaces, complex multidimensional geometries resembling intricate twisted loops where strings thread through to acquire additional mass. These extra dimensions are not mere fanciful inventions. As early as the year 1919, Theodore Kaluza proposed a 5th dimension to unify gravity and electromagnetism. Subsequently, each new force required an additional dimension, compactified tightly at the Planck scale. To eliminate negative probabilities, a total of 9 spatial dimensions plus time, making 10 in all, were needed, and M-theory added the 11th. Calabi-Yau manifolds visualize this, featuring thousands of possible loops for strings to wind around. The Planck tension, equivalent to 10 to the power of 39 tons, keeps the strings contracted, preventing infinite energies. The minimum energy of a string is 19 orders of magnitude greater than that of a proton, but quantum fluctuations cancel out to maintain overall balance and stability. Supersymmetry, often abbreviated as SUSY, serves as a key component. Every particle has a superpartner, bosons paired with fermions. This resolves the hierarchy problem by cancelling quantum chaos. In string theory, bosons and fermions form pairs, leading to superstrings. Supersymmetry unifies the forces, electromagnetism and the weak force already merge at high temperatures, the strong force joins at even higher energies, and with superpartners, all forces equalize at the Planck energy scale. In the year 2025, although the Large Hadron Collider, LHC, has not yet directly detected superparticles at 13.6 tera-electronvolts, TeV, new limits from the ATLAS and CMS experiments indicate they may be heavier or interact more weakly, and the upcoming high-luminosity LHC will extend these boundaries significantly further. Regarding experimental verification, The primary challenge stems from the Planck energy being a trillion times higher than what the LHC can achieve, which peaks at around 6.5 TeV per beam, far too low for direct probes. Yet, in the year 2025, the second data release from DESI, DR2, shows dark energy diminishing over cosmic time, consistent with string models involving dual spaces and T-duality, potentially marking the first observational evidence. Physicists from Virginia Tech and the State University of New York have published models where string theory explains this dynamic dark energy, influenced by Planck scale effects and the universe's overall size. While the LHC has not found supersymmetry directly, tighter constraints challenge simpler models but open pathways to more intricate ones, including proposals for tabletop experiments to detect novel quantum interference patterns. In the context of black holes, string theory describes them as fuzzballs, tangled balls of vibrating strings without a central singularity. Particles falling in immediately integrate into the structure, resolving the information paradox. Large black holes are less dense than water. A distance duality proposed in 1988 by Overbeck and Vafa states that light strings perceive a large universe, heavy strings a small one, but the physics remains identical in both views. Concerning the origin of the universe, string theory eliminates the Big Bang singularity. At the Planck length, temperature reaches a maximum and then decreases, providing a natural limit. Preceding the Big Bang was an inflationary phase, where colliding strings release dimensions, inflating three spatial ones we experience today. The Big Bang itself represents an explosive event birthing a multiverse of possibilities. As we conclude this extraordinary journey, despite the remaining mysteries that continue to intrigue us, string theory stands as a masterpiece of mathematical beauty, as Stephen Hawking once remarked, too elegant to be incorrect. In the year 2025, with insights from DESI and advancements in bootstrapping methods confirming string amplitudes, we are closer than ever to achieving a unified theory of everything. Thank you sincerely for joining us on this exploration, and we look forward to meeting again in future discoveries that await.